Welcome to this AP guided practice on homogeneous and heterogeneous equilibria. So we're going to take a look at each one of these today and some of the parameters around how to work with them to solve problems. So homogeneous equilibria, all reactants and products are in the same state of matter. Either they're all aqueous or they're all gas. We don't have equilibrium situations generally that are going to be outside of those two parameters. One of the big things to remember, or the big things to know, is that partial pressure is proportional to molar concentration, but they are not equivalent. And so one thing that we need to know is that Kc is not equal to Kp, but they are related, and we're going to take a look at that today. So the first thing asks us to write the equilibrium constant expression for using pressure for the following reaction, this just generic reaction. And so we've already done this, and we know that Kp excuse me, is going to be equal to the partial pressure of our products raised to the coefficient of those products. So the partial pressure for C, the partial pressure for D. This is just the generic one over our reactants. So just to re-emphasize, all of these are our coefficients, those exponent values. So if we want to be able to go between Kp and Kc, we actually have an equation that we can use to do that. And so what we find is that Kp is equal to Kc times RT delta N. So delta N is going to be the change in the moles of the gas, and so it's going to be moles of product minus moles of reactants. Our R value that we're going to use for this is going to be the 0.08206 liters atmospheres per mole Kelvin. And temperature, of course, in any gas situation is going to be in Kelvin. Okay, so let's go ahead and work a problem. So this one asks us, what is the Kp for the reaction if Kc was determined to be 23 at 1100 Kelvin? And so we're going to actually solve for Kp. So let's put those numbers in. So Kp is equal to 23 for our Kc value times RT times our temperature raised to the power of delta N. So we need to determine delta N. So for our delta N, our products have 2 moles of gas, 2 total moles of gas. So we're going to say 2 moles minus, and we have 1 mole of oxygen and 2 moles of the sulfur dioxide, and so that's going to give us a total of 3 moles. Okay, so products minus reactants, and that gives us a -1. And so we're going to put this to the -1. We're just going to go ahead and plug that in our calculators, and that should give us a smaller number, and I get 0.25. Again, remember our K values when we're dealing with equilibrium do not have units. Okay, so that's for if we're working with a homogeneous situation and we want to go between concentration and pressure values if we want to know what those are. For a heterogeneous equilibria, not all reactants and products are in the same state of matter. Some are going to be liquid or solid, and so we have to determine what we are going to do with all of these different substances. One thing that we really have to know, put some space down here, is that our pure solids and liquids have constant concentration and are not written in the equilibrium expression. Okay. This becomes really important when we're talking about solubility equilibrium, which we are going to get to later in this particular unit. So they don't go into this situation. Basically, they don't have a concentration. Okay. They just are a solid or just a liquid, but they aren't part of the pressure or the aqueous solution. So if we're going to take a look at something like this, we want to evaluate what do we have that can go into the equilibrium situation. So in this first one, for A, it says write the equilibrium constant expression for concentrations and pressure for the following reactions. And so in this situation, we have CO2 as a gas, but both of these other two, the magnesium oxide and the magnesium carbonate, are solids, and so they're not going to be part of that equilibrium expression. And so what we do is we write this as Kc is equal to 1 over the concentration of carbon dioxide. That is the only one that's going to go into there, is going to be that carbon dioxide, okay, because it's the only one that's in a form that's going to work. With Kc then, or excuse me, Kp, same thing, but now for pressure. So 1 over the partial pressure of carbon dioxide. No coefficient, so we don't have any exponents. All right, let's take a look at B and do the same thing for that. You can pause and try it first yourself. So in this particular situation, we have H2O as a gas and O3 is a gas. The other two are solids, and so they're not going to apply to the overall situation. So it's just going to be these two, not the other two. Still important for the reaction, but not for the equilibrium. So the concentration is going to be products, so O3 cubed over H2O squared. And then for pressure, Kp is the partial pressure of O3 cubed over the partial pressure of H2O squared. Okay. There are some practice problems for you to try and apply some of these, and we will talk about those a little bit more when we're back together in class.